Hello friends, welcome to Electronic Circuit Hub. So today we will understand buck converter. We will realize the buck converter circuit. We will understand buck converter steady state analysis. What is steady state analysis of buck converter? Then we will see what is small ripple approximation for buck converter. Then we will see what is inductor volt-second balance for buck converter. Then we will see what is capacitor charge balance for buck converter, and then we will derive the formula for transfer function of buck converter. What is the transfer function? That is ratio of output voltage to input voltage. So what is the transfer function for buck converter? We will also derive a formula for inductor volt second balance. We will also derive a formula for capacitor charge balance. So this is gonna very interesting video today. So let us start now. So let us first understand what is small ripple approximation, right? What is small ripple approximation and why it is used in buck converter circuit realization, right? So you can see here, let us understand the basic circuits for buck converter. So here I have drawn a basic circuit of buck converter. This is your source voltage, right? And then we have a switch, and this is the node A of switch, and this is the node B of switch. Then we have inductor, which is current flowing through inductor is IL over time period T, and voltage across inductor is VL over time period T. And then we have a capacitor, and then we have a load resistance RL, and then we have a output voltage VO over a time period. So this LC forms a low pass filter which pass a low frequency signal, and it block the high frequency signal of your high frequency switching noise of your buck converters, right? So let us understand small ripple approximation of buck converter. What is small ripple approximation, right? So you can see, this is the output voltage of buck converter. So there is a graph between VO, that is output voltage, over a time period T. So you can see there is a two terms here. One is the DC component, that is VO, DC component, that is VO, and you have some ripple voltage, which is this, right? Which is this. So your VOT of your buck converter equal to VO plus V ripple over time period T. So what is VO? VO is DC components, which is having pure DC. It is having pure DC, and it is the output of your buck converter. But along with DC, we have some ripple component, high frequency noise or high frequency ripple component. Okay, so small ripple approximation says that since V ripple is very less than V out, so you can ignore this term, right? V ripple. So here you can ignore this term, and your VOT equals to V output only. Your VOT equals to V output. So hope you understand what is small ripple approximation and why it is used in buck converter realization or any converter realization. It is very important to understand what is small ripple approximation, right? Now you can see this is the buck converter circuit. We have already seen uh, the components of this circuit. This is supply voltage, then we have a switch which is having node A and node B, and then we have inductor here, and current flowing through inductor is IL over time period T, and voltage across inductor is VL over time period T. And then we have capacitor, and which current flowing through this capacitor is ICT over a time period T. And then we have output voltage VO. This is VOT over a time period T, and this is load resistance. All right. Now let us assume when switch is at position A, when switch is at position A, right? So when switch is at position A, SW at A, then we have a supply voltage, and then we have inductor connected here, then we have a capacitor, and then we have a load here, right? So when switch is at node A, that means your supply voltage charges the inductor through its peak value, and it also delivers the load. Okay, now let us assume when you switch at node B, then this supply voltage Vs behaves like a open circuit. Then during that particular point of time, this is switch is connected here, you can see node B, then this behaves open circuit, and at that point of time, this energy stored in the inductor, energy stored in inductors uh, supplies the load. Okay, deliver the load current or supply, fulfill the requirement of the load, right? So hope you understand how buck converter looks like, and what is the function if switch is connected at node A, and what is function when switch is connected at node B. Okay, so this is basic realization of a buck converter, how buck converter looks like, and what is the behavior of buck converter, right? Now let us understand when switch is at node A. That means your inductor is connected to the supply voltage, and it is also connected with a capacitor C and load resistance RL. So now when switch is at node A, when switch is at node A, now we have to find out what is the voltage across this inductor. The polarity for this uh, voltage across this inductor is plus here and minus here, and voltage across this inductor is VLT, right? VL over a time period T. So now we will find what is the voltage across this inductor. So voltage across this inductor is VLT. And what is the VLT? If you want to apply KVL in this loop, right? Sorry, KVL in this loop. So you can find VLT equals to Vs, the source voltage, minus VOT, output voltage, right? So voltage across during turn on time, or when switch is at A, voltage across inductor is Vs minus VOT, right? So if you do small ripple approximation, you can find the voltage across inductor VL. You can neglect this term time period T. VL equals to Vs minus VO. That means source voltage minus VO. That means when your switch is on or switch is at position A, the voltage across inductor would be your supply voltage minus your output voltage, right? Now let us understand the current for inductor. So if you want to find out the current flowing through this inductor, that is ILT over a time period T. So how will you find? You know that the voltage across inductor is VL over a time period T equals to LDIL T by dt. That means VL equals to LDIL by dt. And now if you find out this derivative, if you want to find out this derivative DIL by dt, okay, so you will find this VLT divided by L. So you know that voltage across inductor is Vs minus Vo from here, right? Vs minus Vo divided by L. So this is the current flowing through the inductor, right? So inductor current changes with a constant slope. We will understand how inductor current changes with a constant slope, right? Now we will understand what is the behavior of buck converter when SW at position B, right? When switch is at position B or when switch is off. So we have already seen the supply voltage. We have like open circuit, then we have inductor, and then we have a capacitor, and then we have this circuit, right? This circuit. Now we will realize this circuit, and we will find out the voltage inductor voltage now. Okay, so for this circuit, if you apply KVL, the voltage across inductor VL over a time period T equals to, this is minus VOT, since here we have output voltage of VOT over a time period T. So if you do a small ripple approximation, the voltage across inductor is minus VO, right? So you can understand that during turn of time of your switch, that or when your switch is at position B, the voltage across inductor is minus VO. That means the voltage across inductor is output voltage, right? If you want to find out the inductor current during turn off time of switch, or your switch is at position B, so you can find VL equals to LDIL by dt, and this time you can find out DIL by dt, that means this derivative, and you can find VL divided by L. If you do small ripple approximation, you can neglect this term, and you will find, since VL equals to minus VO divided by L. So that means current flowing through inductor is minus VO divided by L. So now we know that when switch is at position A, what is voltage across inductor? When switch is at position A, what is current across inductor? When switch is at position B, what is voltage across inductor? And when switch is at position B, what is current across inductor? So these all things now we already derived, and we have got some formula, right? Let us use this formula. So let us derive the inductor voltage and current waveform, right? So this is the inductor voltage and current waveform, you can see here. So this is the voltage waveform, which is visual over a time period T, right? This is inductor voltage waveform, and this is inductor current waveform, right? So you can see, let us say this is time period is DTS. D stands for duty cycle and TS is a total time period, right? So this is 0, and from 0 to here, this time period is DTS, and from DTS to this time period is D prime TS. D prime equals to 1 minus D. Okay, 1 minus D. So during turn on time, or during the time of DTS, the voltage across inductor is Vs minus Vo. Okay, that means we have some positive voltage here, and during turn off time of switch, or the time duration of D prime time of TS, the voltage across inductor is minus Vo. We have already derived this. Now the current across inductor is during DTS, the current across inductor is, the slope of the current is Vs minus Vo divided by L. We have already derived this. And during D prime times of Ts, that means total time period, the slope current for inductor is minus Vo divided by L. This we have already seen. And this is the positive slope, and this is the negative slope. And let us say if there is some DC current flowing through inductor is I. This is the DC current I which is flowing through this inductor. So let us see what is the ripple inductor current. So you can see from here, this is the DC current flowing through inductor. From here to here we have a ripple inductor current which is called delta IL. This is delta IL, right? So if you want to find out the ripple inductor current, what is the ripple current flowing through this inductor, you can find it by using this formula. 2 delta IL equals to 2 delta IL equals to this Vs minus Vo divided by L. That means this slope into the time period, slope into the time interval, right? So you can find this delta IL. So what is the slope? Slope is Vs minus Vo divided by L into what is the time interval? Time interval L, D times Ts, where D is duty cycle, right? So if you want to find out now delta IL, Vs minus Vo divided by 2L, 2 goes here, and dTs, right? And by using this formula, by using this formula, you can find your inductance value, which is equals to Vs minus Vo divided by 2 delta IL. This goes here and this goes here over a time period Ts. So by using this formula, this and this, if you know what is the allowable ripple current of your inductor, you can find the value of your inductor. While if you know the inductance value, you can find the ripple inductor current. Okay. So by using this formula, you can find both inductor value and ripple inductor current. So this is very important formula to understand how it governs. And now let us understand inductor current during transient turn on time. When suddenly Now let us understand inductor current during transient turn on time, right? So this is inductor current IL and with reference to time t. So you can see here a 0. The first inductor current is IL, which is 0 for a time period 0. This is 0, then is increases gradually, then again decreases, then it again increases, then it again decreases. So you can see the your increasing slope is Vs minus Vo divided by L, and your decreasing slope is minus Vo divided by L. These two we have already derived, right? So you can say that the current the current across your inductor cannot change instantaneously, it increases gradually, right? Now let us understand very important uh, term, that is inductor volt second balance. What is inductor volt second balance? So so we have already derived the formula for inductor voltage with respect to time. So for time period dts, your inductor voltage is Vs minus Vo, and for time period d prime time ts, your inductor voltage is Vo, right? So if you want to find out, if you want to apply a inductor volt second balance, you have to find out the area under this curve. So you have to integrate this both positive cycle and negative cycle. Let us assume the area under this curve is x. Let us assume the area under this curve is x. So x equals to 0, and your time period is total time period is ts. So you have to integrate 0 over time period ts and vl over t. Okay, so you have to integrate this vl over t. So you know that what is Vs minus Vo for a time period dts minus Vo for a time period d prime times ts. If you, so the average voltage of inductor is, this is x divided by time period. So you already know what is x, and what if you divide your time period ts, you will get Vs minus Vo. You will divide here ts, right, and you will divide here ts. So this get cancelled. Okay, Vs minus Vo into d minus Vo into d prime, right? So if you further solve this, Vs into d minus Vo, if you take a common d plus d dash, and we already know d plus d dash equals to 1. So this term would be 1. Then you have only d into Vs minus Vo equals to 0. And what is your Vo? Vo equals to duty cycle time of Vs. So this is basically a relation between your input voltage and your output voltage, and this is basically a transfer function. If you want to find out the transfer function, Vo divided by Vs, which is equals to d. So by looking this formula, you can see in buck converter your output voltage is directly proportional to the duty cycle duty cycle times of your input voltage. So this is very important parameter you need to pay attention here. What is the output voltage of your buck converter, or what is the transfer function of your buck converter? So your output voltage of buck converter is directly depends on the duty cycle times of your input voltage or your source voltage. So hope you understand what is inductor volt second balance, and how do you find the output voltage for your buck converter, and how do you derive the transfer function for your buck converter, right? Now we will understand one more very important parameter, that is capacitor charge balance. What is the capacitor charge balance, and what is the behavior of capacitor in the buck converter, right? So this is very important parameter we will understand now. So if you want to find out current across the inductor, which is given by IC over a time period t equals to C into dVCT divide over a time period t divide by dt. So you already know this is VC, voltage across capacitor would be VC over a time period Ts minus VC over a time period 0, which is equals to 1 by C. You have to integrate this, right? You have to integrate this, so this 0 to Ts over this Its, right? Since this is derivative, so if you want to find out your dVCT divided by dt, you have to integrate this. So VCT equals to, you have to integrate your ICT, then you can find your, since this is 0, the net change that the net change in capacitor voltage is 0 in buck converter in steady state condition. In steady state condition, the net change in capacitor voltage is 0. So this term will be 0. So this term will be 0. Then you have 1 by Ts, 1 by Ts 0 over time period Ts ICT into dt. So what you can find from this formula, the net change, the net capacitor current change in buck converter is 0. So right, so you can summarize it, the net change in capacitor voltage is 0 for a time periodic signal, and in steady state condition the average capacitor current is 0. So this is very two important parameters you need to understand, and you need to know that the net change in capacitor voltage is 0 for a time period, for a periodic time signal, and in steady state condition the average capacitor current is 0. So hope you understand what is buck converter, how do you realize your buck converter, what is the steady state condition, what is small ripple approximation, what is inductor volt second balance, what is capacitor charge balance, and how do you derive a transfer function of buck converter, how do you derive a output voltage of buck converter. If you have any question, feel free to ask me in comment section. Thanks for watching this video.